Hey everyone, in this video I wanted to discuss the OSPF adjacency process. And there's several things I want to cover in this video. First off, I want to make sure I go over what are the different requirements for two routers to form an adjacency. So I'll cover things like, does the OSPF process ID need a match? Can the interfaces of these two routers be in the same or different subnet? And things of that nature. After that, we'll then move on to discussing the different OSPF adjacency state. So I'll talk about what are the different states, what happens in each of those states, and following that, we'll then do a packet capture so that I can show you the different messages that are sent out by each router during each OSPF state. And then finally, we'll wrap up by running a few debugs on these boxes so that we can see what are some of the outputs that these routers send when they are initially forming an adjacency state. All right, so let's talk about the adjacency requirements. And so I've listed them out here. The first one is that the two routers have to be in the same exact subnet. If they're not, you're going to see a warning message letting you know that they're not in the same subnet and they will fail to form an adjacency. After that, we need to make sure that the hello and dead timers must match as well. The hello and dead timers are sent in the hello updates. So that's how we know what the hello and dead timers are from our neighbor. And they have to match. As well, we also have to make sure that the areas match as well. So if router 1 is in area 1, then router 2 also has to be in area 1 for them to form an adjacency. But keep in mind that the areas only have to match on the interface that we're trying to form an adjacency. Obviously, the routers themselves can have other interfaces that are in other areas. As long as the interface that is forming an adjacency with the other router is in the correct area, that's all that matters. We also have to make sure that between the two routers, the router IDs are unique. If you have duplicate router IDs, that's going to create all sorts of problems in your network. And finally, if you've got any kind of authentication, they obviously have to match as well. And keep in mind that the OSPF process ID does not need to match. And this is something that I see a lot of people get wrong. I'm not really sure why. I think a lot of times people happen to learn EIGRP first. And in EIGRP, the AS number or the autonomous system number has to match between two peers to form an adjacency. But for OSPF, that is not the case. The process ID is strictly local to each box. And if you actually take a look at an OSPF hello packet, you'll see that there's no field anywhere in that packet where we can store the process ID. So that's why it's not an actual requirement for two routers to form an adjacency. All right, so let's move on to talking about the different OSPF states. So I've listed out the 7 main states. There's technically 1 or 2 more, but those aren't really applicable in like 99% of circumstances. I think the only time you ever see those other 2 states is if you're using a specific OSPF network type, which not many people use. So just focus on these main 7. These are probably going to be the ones that you see out in the wild. So the first state is the down state. And so this is going to be the first OSPF neighbor state. And in this state, no hellos. It basically means that we haven't received any hellos from this neighbor, but we can still send hellos to that neighbor. And so the main situation where you're ever going to see a neighbor in the down state is usually if we already had an established adjacency with a peer or another neighbor, and we didn't receive a hello from that neighbor within the dead interval time. And so we then declared that neighbor essentially dead, so we moved them from a full state to a down state. All right, so let's move on to the next state. The next state is the init state. Basically, as soon as we receive a hello packet from a neighbor, we're going to place them in the init state. And we're going to keep that neighbor in the init state until we see a specific signature in the hello packet from that neighbor. And what we want to do is we want to ultimately see our own router ID embedded in our neighbor's hello packet. And what that ultimately means, is that our neighbor, if they know our router ID, that means they have received our hello. So once they start embedding our router ID in their hellos, it means that we have successfully reached two-way communication. All right, so we move to two-way state once we've established bidirectional communication between the two peers. And once again, that happens as soon as we start seeing our own router ID in our peer's hello message. All right, so we move into the two-way state. Now, once again, in the two-way state, we have established bidirectional communication between the two peers, and we know that we have bidirectional communication due to the fact that we see our own router ID in our peer's hello message. At the end of the two-way state, the DR and the Bdr election takes place whenever we have some type of broadcast network. Now, I'm not going to cover the DR and Bdr election in this video. That's a separate topic. If you guys want me to make a video on that, I'll be more than happy to. Just let me know in the comments. But that happens at the end of the two-way state. So after we finish with the two-way state, we're going to move on to the XStart state. And in the XStart state, we establish a master-slave relationship between the two peers. And this is very important. This master-slave relationship has absolutely nothing to do with the DR and Bdr election. This is a completely separate thing, and it serves a completely separate purpose. And so the router with the highest router ID becomes the master. And the master is responsible for setting the initial sequence number and for incrementing the sequence number. And you're probably, when you hear the word sequence number, I'm sure two things come to your head. You're probably thinking of either sequence numbers within TCP, or you're thinking of sequence numbers in LSAs. And I want to tell you that these sequence numbers are a completely separate concept, right? Because there's no TCP in OSPF. OSPF doesn't use TCP. And the sequence numbers in LSAs just let you know, how recent or new your LSA is. So every time an LSA gets updated, you increment the sequence number. These sequence numbers that I'm talking about are used for just one very simple purpose. They're just a very, it's just a very simple acknowledgement system, so that anytime our peer sends us a certain packet, he's going to set a sequence number. And when we receive that packet, the way we acknowledge it is we're going to send back another packet with the same exact sequence number. And so that's all we're using these sequence numbers for. And keep in mind that it's always the master that sets the initial sequence number. So, let's say hypothetically that, the master sets the initial sequence number to 200. He's going to send that to the slave. The slave acknowledges that by sending another packet with the same exact sequence number of, I think, what did I say? It was 200? I already forgot. So he sends back a packet with the same exact sequence number. Then after the master receives that, he'll then increment it by 1 and go to 201 and send a packet with a sequence number of 201. The slave will then acknowledge it with a sequence number of 201. If that seems a little confusing, don't worry. I've got some slides that explain that a little more later on in this video. All right, so after we've held the master-slave election in the XStart state, we then move to the exchange state. And in the exchange state, we exchange database descriptor packets. And if you aren't familiar with database descriptor packets, these are basically summaries of your entire link state database. They don't contain the LSAs themselves, right? These are not full LSAs. They're basically just the LSA headers, or think of it just as the link state IDs. It's just a way to let our neighbor know that we've got these certain LSAs, but we're not actually sending them all these LSAs. It's just a quick summary or a quick snapshot of our entire link state database. All right, so think of them as just a short and sweet summary of the link state database. So after we finish exchanging all of our database descriptor packets, we're going to move into the loading state. And in the loading state, based off the information that was received from these database descriptor packets, we're going to then send link state requests for each missing LSA that we don't have. So then we'll send a link state request to our peer, and our peer is going to respond back with a link state update. And that link state update is what's going to have the complete LSA. So that's the actual LSA that finally gets sent to the peer that's requesting it. And when the peer receives that LSA, he needs a way to acknowledge that LSA. And we've got two different ways of acknowledging LSAs. We can do an explicit ACK or an implicit ACK. With an explicit ACK, we send a specific OSPF packet, which is a link state acknowledgement packet. And an implicit ACK is that we send a duplicate of the LSA that is being acknowledged. So if our peer had sent us an LSA for the 192.168.10.0 network, we just send that same exact LSA back to him, and that lets him know that we successfully received that LSA. So you can use, the router can pick how it wants to acknowledge it. These are the two different methods. And finally, once we have sent all of our LSAs to our peers and everything's been acknowledged, the routers will move into the full state, and in the full state, routers are fully adjacent with one another. So this is the final state that you want your routers to be in. It means everything's working, everything's good, the adjacencies are up, you haven't run into any issues with them during the adjacency process. So this is ideally what all neighbors should be in, or the state that all neighbors should be in. So that was just a high-level overview of what the OSPF state process looks like. What I want to do now in the next few slides is kind of walk you through step by step what all of that actually looks like with kind of nice detailed diagrams. All right, so in this diagram, we've got two routers. We've got R1 on the left with a router ID of 1.1.1.1, and on the right, we have R2 with the router ID of 2.2.2.2. And so they're going to start out in the down state, so we can just assume that maybe OSPF is not enabled. But once we enable OSPF, you'll see that they move into the init state. And once we enable OSPF, they're going to start sending hellos to one another, and they're going to send it to the multicast group of 224.0.0.5. And so, whenever you configure OSPF on an interface, that interface is automatically going to subscribe to that multicast group so that they can receive multicast hellos from other neighbors and process it at the CPU level. So R1 is sending hellos to R2, and R2 is sending hellos to R1. Now, the second we receive a hello from our neighbor, we're going to start embedding the router ID that we got from that hello packet into our own hellos. So you can see here in this diagram, R1, it received a hello from R2, and so in R1's hellos, he's going to put in the router ID of R2. And so we've got this hello packet here, and he's going to send it with the router ID of R2 and send that to R2. And R2 is going to do the same thing. He received a hello from R1, so now he knows the router ID of R1, and now he's going to embed it in the hello packet that he sends out to R1. And so once we get these hello packets, we'll then see our own router ID within the hello packet. So then R1 and R2 can then move into the two-way state. That's how we confirm that there's bidirectional communication. Now, at the end of the two-way state, we hold the DR and Bdr election. And so whoever's got the highest router ID, which in this case is router 2, he's ultimately going to be the DR, and then router 1 is going to be the BDR. So after we finish that election, we move into the xstart state. Now in the xstart state, if you recall, this is where we set up that master-slave relationship. And the way that it actually works is that both routers assume that they're the master. So R1's going to tell everyone, hey, I'm the master in this network. And R2 is going to be like, no, man, I'm the master. And so what they do is, because they both think that they're the master, each router is going to send out a database descriptor packet with what they think is the initial sequence number. So they pick some arbitrary sequence number. I picked 100 and 200 in this case. So R1 thinks the initial sequence number should be 100, and R2 should be thinks it should be 200. And so they send that packet out to their peers. And eventually they hold the election to determine who the actual master is. And the deciding factor for who the master is the same thing for the DR and BDR election. And that's going to be whoever has their highest router ID will be the master. So in this case, R2 is going to be the master. And so R1 knows that he's going to be the slave. And so if you recall, R1 sent an initial database descriptor packet with a sequence of 100. And R2 sent it with the initial database descriptor packet with a sequence of 200. And so what's going to happen is that now that R1 knows that he's the slave, he has to send out a database descriptor packet matching the sequence number to that of the R2's packet. So since R2 sent it with a sequence number of 200, R1 has to match it with a sequence of 200. And this database descriptor packet will contain a list of LSAs that R1 knows about. So R2 sent a packet. R1 is essentially acknowledging it, saying, I'm acknowledging I received it by sending another packet with the same exact sequence number. And he's going to include some information about his link state database, a few of his LSAs. So once R2 gets that packet back from R1 and sees that R1 has acknowledged his sequence of 200, he's going to increment the sequence number to 201, and he's going to send a new database descriptor packet to R1. And once again, within this packet, he is sending information about his linked state database. So he's going to send a summary of all of his LSAs. And so he sends that database descriptor packet with a sequence of 201 back to R1. R1's going to receive it. He's going to acknowledge it by sending a database descriptor packet matching that sequence number of 201. And within that sequence packet, within that database descriptor packet, he's embedding his information about his linked state database as well. So he's going to highlight all the LSAs that he knows as well. And so they're going to keep repeating this process. So once R2 gets that packet from R1 with a sequence of 201, R2 is going to then increment it by 1 again. So he's going to send it with a sequence number of 202 this time. And he's going to fill out the remaining LSAs. And he's going to send that to R1. R1's going to acknowledge it by sending a new database descriptor packet with a sequence of 202 as well. So they're just going to keep going back and forth until they have sent all the information about their database to their peers. And remember, these sequence numbers, they're nothing more than just a simple acknowledgement system for these database descriptor packets. They serve no other purpose. So R2 will continue sending those database descriptor packets and incrementing the sequence number until he no longer has any LSA summaries. And at this point, we will transition to the loading state. All right, and in the loading state, R1 will take a look at all the database descriptor packets that R2 sent it, and it will see what LSAs R2 has that he doesn't. And so he'll populate a list of LSAs that R2 has that he doesn't, and he'll send a linked state request for all of those missing or outdated LSAs. So he sends that linked state request. In this example, I did 192.168.1.0. So he's just picking this one specific LSA that he doesn't have. He sends that to R2 asking for that. R2 sends a linked state update for that LSA, and he sends that back to R1. And once R1 gets it, he sends an acknowledgement. And if you remember from the earlier slides, there's two ways to acknowledge that linked state update. We can send an explicit acknowledgement, which is we send a linked state acknowledgement packet, or we can do an implicit acknowledgement. And the way we send a implicit acknowledgement is we send that same exact LSA back to R2, and that lets R2 know that we received the linked state update for 192.168.1.0. So here's an important thing to note. The way I've described it, it makes it seem like, in the exchange process, we send the LSA summaries to one another, and then only once we're done sending all of our LSA summaries will we move into the loading state and start requesting and sending full LSAs. And that's kind of the simple way to explain it, but in reality, what you'll see is that the exchange and the loading phase are kind of blended together. And what I mean by that is that when we start the exchange process and we start sending database descriptor packets, the second that one of the routers sees an LSA summary for an LSA that he doesn't have, even if they're still in the exchange state and they're still exchanging these summaries and they're not finished, he can still send a linked state request in the middle of that process for any LSAs that he is aware of that he doesn't have. So you'll see that even though the exchange process hasn't completed, we're already kind of in the loading phase because we're already requesting and sending LSAs to one another. So just keep that in mind when we look at the packet captures. You'll kind of understand what I'm alluding to with this slide. All right, so once there's no further LSAs in the linked state request list, the peers will then move into a full state. And at this point, the adjacency process is complete and everything's good to go. All right, guys, so I set up two routers similar to what I had in the slide deck, R1, R2 with the router ID of 1.1.1 and 2.2.2. And I just did a packet capture just to go over what the OSPF state process looks like at a packet level. And so I do want to point out a couple things when it comes to IP addresses. So the 192.168.1.1 address is going to represent R1, and 192.168.1.2 is going to represent R2. All right. So let's take a look at this packet by packet and see what exactly is happening. And hopefully by going over this in Wireshark, you can get a better understanding of how this whole process works. And so you can see that I enabled OSPF right at this point, starting at packet 82. And hopefully you guys can see this and it's not too small. I guess I can zoom in a little more. Hopefully that's readable. So at this point, 192.168.1.1, which is R1, sends his first hello packet onto that link. And if you look at that hello packet, you can see that we include what's our router ID, the area number, and a few other things that are important, as well as, who's the designated router and the backup designated router. And so you can see here that we actually haven't filled this information out because we haven't held that election. But we carry important information in these hello packets that are necessary to determine if we can actually form an adjacency. We also send the hello and dead intervals. We got to make sure that matches as well. So R1 sends that first packet, and I want you to focus on this OSPF hello section and notice how there's no other information in here, all right? So then if we go down to the next packet, we can see 192.168.1.2 sends his first hello. So that's R2 initializing his OSPF process on that link, and he's sending out his first hello. So he sends out a hello. He's going to include his own router ID, and you can see here that the DR and the BDR have not been filled out, and there's no other information, right? But at this point, we know that R1 sent his hello and R2 received it, assuming that there's no drops in the network. And we know R2 has now sent his hello and R1 has successfully received it. So if we go to the next packet on packet 84, we can take a look at R1's hello now. So we know that R1 has received a hello from R2. So what does R1 have to do after he's received a hello from his neighbor? Well, he's going to start embedding the router ID of R2 within his hello packet. And so you can see here under the active neighbor section, under the OSPF hello packet, we're now putting our peer's router ID into the hello packet. So when R1 sends this out onto the link and R2 gets it, R2 is going to see his own router ID in the hello packet, and he's going to move into the two-way state. Then the packet below that, R2 is going to do the same thing. So he's going to start embedding R1's router ID into his hello packets. So once R1 gets that, R1 is then going to move into a two-way state. All right, so they moved into a two-way state at this point. So they'll hold the DR and the Bdr election. Then eventually they're going to send that first database descriptor packet, and that's going to start the xstart state. And so you can see here, R1 happens to be the first router on this link to send a database descriptor packet. And if you recall, when I was talking about this whole process, both routers by default will assume that they are the master on this link. And so if we look at this OSPF database descriptor packet, you'll see this little flag right here. And this flag, if it's set to 1, it implies that this router thinks that he's the master. And so R1 thinks he's the master, and he's going to pick an arbitrary number to set the initial sequence number. And so this is the database descriptor sequence number, and he's picked 3721. All right, so he thinks that's what the starting sequence number should be. If we go to packet 104, right below that, R2 is doing the same exact thing. He thinks he's the master, so he's going to set that flag to 1, which means he thinks he's the master, and he thinks that the sequence number should be 2673. So just keep that in mind. R2 thinks the sequence number should be 2673, and if we go back to the R1s, he thinks it should be 3721. Now, we know that R2 has the higher router ID because his is 2.2.2.2, which is higher than 1.1.1. And that ultimately means that R2 thinks, or that ultimately means that when we hold this election, R2 will win the election and he will be the master. So they basically held the election here. You don't actually see it. They just kind of understand based off the router IDs. So R1, he's going to send a database descriptor packet, and you'll see that he sets it to a value of 2673. And that value is important because that's the sequence number that R2 set. So if we go back to packet 104, R2 initially set it as 2673. So the way that the slave essentially acknowledges that packet and acknowledges that he's the slave, he's going to send a database descriptor packet with that same exact sequence number. Now within this packet, he's going to include a summary of his entire link state database. He's obviously not going to be able to fit it all into one database descriptor packet, but he's going to squeeze in as many as he can based off of whatever the MTU of that link is. And you can see here, these are all the LSAs that he has, and he's sending that over to the neighbor. And keep that in mind, these are not the actual full LSAs. these are just summaries of the LSA. So he's just providing basically just the link state IDs and a few other bits of information about the different LSAs. So we've got a couple of router LSAs, a couple network, and then a whole bunch of external LSAs. So basically what he's doing now is he's got all this information in his link state database. He's sending it back to R1, and he's acknowledging R1's packet by matching his sequence number. R1 is matching R2's sequence number. So R2 is going to get that packet, and he's going to then send a new database descriptor packet. So if we go to 106, packet 106, he's going to increment the sequence number to 2674. So he incremented it by 1, and now he is going to start sending information about his link state database. So he's going to include all of his, type 1, type 2, type 3, type 4, type 5 LSAs to R1, the slave. So he increments the sequence number and includes all of his link state database information. So once R1 gets that, R1 has to acknowledge it and continue to send more information about his link state database. So if you go to packet 107, R1 is going to acknowledge it by matching the same exact sequence number, and then he's going to include more LSAs from his link state database. And also take a look at the master flag. Because the election was held and R1 understands he's the slave, he's going to always set that bit to 0. And so R1 matches the sequence number and he sends it back to R2. R2 knows that R1 received his database descriptor packet and has acknowledged it, so then he's going to bump it up by 1 to 2675 and send that to R1. R1 is going to then do the same thing. He'll match that sequence number and keep including more information about his link state database. And so they're just going to keep doing this over and over again until they've successfully summarized their entire link state database. But before they actually complete that, I do want to highlight one important thing. If you recall in that one slide, I told you that there isn't a definitive line between when we move from exchange to loading, right? Because even though we haven't finished the exchange process, which means we haven't finished sending all of our database descriptor packets, you can see that we send a link state request. Actually, specifically, R2 sends a link state request on packet 109. And the reason he does that is that even though they haven't finished the exchange process, R2, based off the database descriptor packets, already knows that R1 has several LSAs that he does not have. So he's going to right away start asking for those LSAs by sending a link state request. So if we just click on one of these, you can see he sent a link state request for LSA with an ID of 99.0.0.1. And that's coming from the router with a router ID of 4.4.4.4. So he sends a link state request because he already knows he's missing some LSAs. But the whole database descriptor packet exchange process is still going on. So you can see we send another database descriptor packet. Then all of a sudden R1 sends a link state request for several LSAs that R2 has that he doesn't have. And so they're sending these requests and they're still continuing with the database descriptor packet exchanges in the exchange phase. So both phases are kind of occurring at the same exact time. So eventually, once each router gets that link state request, they're going to send a link state update. So R2 got the link state request from R1, so R2 is going to send a link state update. And in an update, we're going to actually send the full LSA. So if we take a look at the LSA now, this is the full LSA. This isn't a summary of it. This is the actual LSA itself. And so we send that link state update. Then R1 sends a link state update. R1 sends another one. So it looks like R1's just going to send a whole bunch more because he has a larger link state database at this point. We're still continuing the database descriptor packet exchange. You can see we're on sequence number 2676. So that's going to keep going for a while. So we'll just keep going down. We're still exchanging LSAs as well with link state updates and link state requests. And then eventually we have to acknowledge that we received these LSAs. So R1 is now sending a ls acknowledge. And he's sending in an ls acknowledge for all of these LSAs. R1 sends another acknowledgement. Then R2 is going to send an acknowledgement back to R1 saying he's received all of R1's LSAs. It looks like we send another update and then acknowledge that again. And so at this point, this is the last acknowledgement. So we have completed the exchange process. We have completed the OSPF adjacency process. We have exchanged all of our LSAs, and we are now in a full state. And so that's basically how it works. I do want to point out one thing. If you look at the last few database descriptor packets, look at this more bit. So anytime this bit is set, we're basically telling our neighbor we still have more database descriptor packets that we need to send you, right? And so once we're done summarizing our link state database, inside the database descriptor packet, we'll send it with the more bit set to 0. That means we are done sending database descriptor packets. We have nothing else to tell you. And so once both neighbors send it with a flag of 0, that means they've completed that exchange process. And now we're exclusively working on just sending requests and updates. And then once that's done, we then move into the full state. So that's basically an overview of how the whole OSPF process works. It's not too complicated once you wrap your head around it. It's just a series of sending database descriptor packets to get an idea of what our peer knows about when it comes to LSAs, and then requesting for those missing LSAs with link state requests, and then getting link state updates from our peer and then acknowledging it. And that's pretty much how the OSPF adjacency process works. Now, I do want to log into some devices and just kind of show you what happens in certain scenarios when you have misconfigurations or missing configurations. So like we'll configure duplicate router IDs and see what happens. We'll try putting wrong subnets and we'll see what happens. So let me bring up a connection to these two devices and we'll take a look at what that looks like. All right, guys. So I've set up two boxes, R1 and R2, just like we had in the slide deck. So R1 is going to be that 1.1.1 router, and he's going to have an IP address of 192.168.1.1. And then we also have R2, which is going to be this guy right here. He's going to be that 192.168.1.2, and he's going to have that 2.2.2.2 router ID. And so what I did really quickly was I enabled two debugs, and I wanted to show you what that output looks like. It should ideally match what we see in the packet capture, although I find that a lot of times these debugs aren't quite as verbose as looking at packet captures. That's the best way to troubleshoot, is looking at packet captures. But sometimes running debugs is a little quicker, and there are times where it's not an option to actually take a packet capture, and whether that's the platform that you're working with, or maybe you don't have a span session, or maybe there's just no control plane capturing feature on your box. Sometimes getting those packet captures is not an option, so the next best thing is running debugs. So there's two main debugs for adjacencies. There's debug IP OSPF, then the process ID, and then hello. So that's going to just capture hello packets. I've enabled it here. A lot of times when I'm troubleshooting, I don't usually enable it, because usually on my boxes, I'll usually have a ton of OSPF neighbors, and you'll see that this just absolutely clutters the logging buffer, because every single hello packet that we send or receive is going to get logged. So I usually don't enable that, but there are times where you may want to enable it if you are not seeing the hellos, or if you want to confirm if one side is sending it and the other side is not receiving it, which might imply that maybe there's another device in the middle dropping those packets. So it can be helpful. I went ahead and enabled it in this case just to show you guys what it looks like. But the main debug that you want is debug IP OSPF process ID, then adjacency. So that's going to give us information about the adjacency itself. And you'll see that as soon as we enable it, before I even enable OSPF on that link between the two routers, you can see that I'm already sending hellos to another neighbor I have on a separate link. So this means that we received a hello from this neighbor, and then you'll see that we've sent a hello to that neighbor. So that's what that output looks like. So if we scroll down a little further, focus on that 192.168.1.1. So here we're sending the hello to R2, and we're going to keep sending it, and eventually we receive a hello from R2 right here. So R2 has finally sent a hello, so we've enabled OSPF at that point. And at that, since we've now received hellos from one another, we can then move into the two-way state, which is shown right here. And so after we move into the two-way state, we'll move into that xstart state. So let's just keep going down. Actually, right before we move into the xstart state, we're going to hold that Bdr election. And so we can see here that R2 wins the election, as he should, because he has the higher router ID. Then we're going to start sending our initial database descriptor packet. And remember, R1 and R2 are both going to assume they're the master at first. So here, R1 is sending a database descriptor packet to 2.2.2, and he's going to send it with a sequence number of 1B03. And he's going to resend it a few times. I'm not sure why he's resending it. It could be he's just waiting for R1 to send his initial database descriptor packet. He's waiting for R2 to send it. So R2 finally sends his initial database descriptor packet. And he's going to set the initial sequence number to 0x39E. So they both have a different idea of, who is the master and who is setting the initial sequence number. They both think that they own that responsibility. Eventually, negotiating is complete, and R1 learns that he's the slave. And so R1 is immediately going to send a database descriptor packet matching the sequence number of R2. So he sends it with the sequence number of 0x39E, which matches what we received from R2 right here. All right. And so at that point, we send that sequence number. We kind of continue to do that process over again and incrementing the sequence number. I don't actually see a lot of that output in here. I'm not sure why it doesn't show that. Maybe the debugs just aren't as verbose as I would like it to be. But eventually we move into the exchange state, or the exchange state finishes actually, and we start sending link state requests to 2.2.2. And we then receive the link state updates from 2.2.2, and then eventually we move into a full state. So that's just what the debugs look like in OSPF. I just wanted to show you guys that just so that you know what to look for if you ever do run debugs on your boxes. But anyways, that's all I had for you guys in this video. Hopefully you guys found this helpful, and hopefully you guys have a much better understanding of how OSPF actually forms an adjacency and what are the different states and processes that we go through before we finally reach an established adjacency.